Okay, great. So good evening to everyone in the UK. Good morning to everyone in North America. And for those joining us on YouTube in the future, thanks for attending this session and watching this video. So this is designing dedicated SQL pools for scale and performance. My name is Miles Cole. I'm a managing data architect at Hitachi Solutions. We do consulting across all of Azure, so everything from Power Platform, data and analytics, modern application development, Microsoft CRM implementations, F&O. It's really everything Microsoft and all the clouds. I've implemented over 15 Synapse environments over the last few years, most of which have involved dedicated SQL pools. Also implemented a few lakehouse type architectures. I love all things Azure, so even infrastructure. I don't like networking. I specialize in MPP architecture and CI/CD. I've got quite a few Microsoft certifications, all the different acronyms. This is my first time speaking at a conference, so extremely excited to have this opportunity. Also first time blogger. I decided to just take care of my last couple years' New Year's resolutions all in the same month. My favorite languages are YAML, Bicep, PySpark, C Sharp, and SQL. I do have a blog that you can check out, milescole.dev. I'll be frequently posting on particularly topics around Azure Synapse Analytics, but we'll also be diving into some CI/CD. I have GitHub and LinkedIn, of course. So now, before we dive into the agenda and drill into these topics, first, why should you care? The basis is you can spend a lot more money than you ultimately need to on Synapse. I see it all the time, and if you don't implement Synapse well, you can end up using a Synapse SKU that's much higher than you ultimately need. And what does that cause? It causes your customers or your business to be spending a lot more on their infrastructure, poor developer experience, potential burnout, poor expectations, expectations not met from a data refresh perspective. In worst case scenario, maybe you end up thinking you need to migrate to an inferior data warehousing platform. So at the end of this session, I'm going to be doing a demo of tuning a large scale query, the 100 million row scale, that takes about 3 hours to run as is on Synapse, the small SKU. And with applying some different principles, I'm going to get it to run in about 10 seconds. So during this session, we're going to be covering different techniques and optimization and design patterns for properly implementing Synapse. Hopefully that'll give you some additional tools in your belt so that you can get more out of your Synapse environment. In terms of the agenda, so we're going to first start with high-level dedicated architecture, table distributions, table indexing, database settings, stats, materialized views, data loading patterns, writing Synapse SQL, optimization demo, and then a Q&A. All right, so let's dive in. So Synapse Dedicated Architecture, and really kind of the motto for this section is that Synapse Dedicated does not equal Synapse or SQL Server. It does share the same heritage and a lot of the same underlying technologies. It also resides on a logical server, but it is fundamentally different. Now, before we dive into those differences, let's talk about kind of position ourselves as far as where we're at in the Azure ecosystem. So within Azure Synapse Analytics, we have this platform as a service that's really designed for analytical workloads at any scale, provides a SaaS developer experience, providing both no-code, low-code, and code-first options. Supports multiple languages, particularly on the Spark side of things. Multiple different form factors, both dedicated and serverless compute options, multiple different runtimes in terms of SQL, Spark, as well as telemetry, big data telemetry compute. Provides out-of-the-box data integration for already connecting to your data lake. Now, for today's session, we'll be focusing exclusively on the dedicated SQL compute option within Azure Synapse Analytics. So first, let's talk about kind of high-level differences in the two different architectures. So we have SMP, which is symmetric multiprocessing, and MPP, massively parallel processing. The SMP, which is going to be Azure SQL Database, MySQL, Oracle, most of your common relational databases. You're going to have multiple CPUs that are used to complete individual processes simultaneously. Now, all of those CPUs are sharing the same underlying memory, disk, all of the physical infrastructure. Whereas on the MPP side of things, there's many different physical infrastructures that each have their own different CPUs that have their own memory and disk. So you have a distributed compute network. And then in the MPP architecture, those different distributions or segments are able to compute using high-speed network. And on the Synapse side of things, it's called the data movement service. And so this foundationally, this is going to be very similar to the concept behind Spark, where essentially you kind of have your driver and executors, and they split up jobs. But that's going to be the core difference between Synapse and Azure SQL Database. Now, from a visual perspective, within the Synapse Dedicated SQL Pool, what we have at the top level here is your control node. And this is what users and applications are actually connecting to. And this is essentially in Spark equivalent to your driver. Now, when queries get passed into the control node, that control node evaluates based off of having information about where data resides and the pattern in which it is stored to then ultimately generate query plans, and will deliver those plans to each of the compute nodes. And then each of those compute nodes execute jobs on each of the 60 data distributions that exist in Azure Storage. Whereas with regular SQL Server, you fundamentally have one physical piece of infrastructure, and now with some tiers in Azure, like business critical, I mean, technically you also have like some internal replication going on between different physical boxes, but kind of the core there is that you have one physical infrastructure, and then with your distributed dedicated SQL pool, you have a collection of many different compute resources that operate on those jobs in parallel to produce big data scale results. So now let's talk about table distribution strategies. So first, what is a distribution? A distribution is essentially an individual segment of your data. And as I mentioned, with Synapse, you have 60 distributions. I believe in like AWS Redshift, which is going to be largely the same architecture. I think you have 100 distributions. So depending on the technology, you're going to have a different number, but the concept is relatively the same amongst all of these. Your likely massive table is broken into very small pieces, and then compute operates on each of those pieces in parallel. So that is a distribution. Now, Synapse gives you the options to pick different methods or algorithms to distribute your data. And these really provide a great opportunity to, if having information or understanding of how your data works and what your kind of business logic looks like, you can distribute your data in an ideal method to improve the performance of your platform. Round robin randomly and evenly spreads the data across the 60 distributions. That's really good for when you don't know your data domain yet. So, you know, you're seeing the data for the first time, you don't really understand joins yet. You just know you need to get it loaded and then start exploring it. When you can't find a good alternate distribution candidate, Some tables may not have prime keys that have high cardinality. We'll talk about later why that's important for other distribution types. Good for quickly landing data, avoiding data skew because it's completely even and random. So all 60 distributions are guaranteed to have nearly the exact same number of rows. However, this is really bad for avoiding data movement. Any query that is not a simple select from an individual round-robin data table will have data movement if you are joining against a round-robin table. It's bad for fast upserts into a staging table simply because data needs to be shuffled around in order to find matches. So now let's look at an example here. So on the left-hand side, we have an order lines table that's round-robin distributed. The right-hand side, product, also round-robin distributed. And let's imagine that we have this query on the bottom left where we are joining order lines.
What?
Product based off of product ID.
Is it ready?
So with product ID,
go ahead, please. Put it in. Thank you.
I added this distribution column. You don't actually see this in the logical table, but this is just symbolic to indicate where the data would likely land. We look at product ID 2 in the order lines table. It exists in distribution 1. And then if we wanted to join this record, product ID 2 to product ID 2 in the DBO product table, you'll see that it exists in distribution 2. So these are different distributions. So that means it needs to perform a shuffle in order to align common records so that it can perform that join. Same thing for all these other records. So 3 to 3, we get another shuffle. And then so the resulting query plan on the bottom left is that both of these source tables are going to be shuffled. And it's estimating that 100% of the query cost is because of that shuffle. And that's bad because that means the data has to be moved from distribution to distribution, essentially reorganized in order to perform the select statement. So now our next distribution type is replicate. Replicate stores your data as round robin in all the 60 distributions, but after the first select statement or even query plan that's generated off of that data will cause the data to be replicated to the compute node. So instead of only having it in each of the 60 distributions, you also have a copy full table on each compute node. Now, DML, so data modification, changes to table structure that does invalidate the replicated table. So there's some important considerations in terms of when you would want to actually use this. So first of all, it's good for minimizing or eliminating expensive broadcast move operations, but it's going to be bad for tables that are updated frequently. And that's because every time data gets updated, it has to rebuild that replicated table cache. And the replicated table cache can only update the replica of one table at a time. So if you have hundreds of tables that are defined as replicate and they're being updated every hour, that cache is going to be constantly spinning and likely will have a long queue of tables to be replicated. So good to be aware of. Also, large tables. General guidance is going to be 2 GB compressed. But if it is a very infrequently updated table, you could get away with replicating an even larger table. You really just need to kind of consider the mix of how frequently is it updated and how big is the table. Also bad for tables that are really hash distribution candidates. Hash distribution, if it is an option, is always going to provide better performance than replicate. So now let's look at this same example. Order lines via product. The only change here is that we've defined the distribution of product as replicate. We have the same query, but now the resulting query plan, you'll see you don't have any shuffles taking place. And that's because this underlying data has been replicated to the compute node. And so the control node has evaluated that all the data exists where it already exists to perform the join. And therefore, it's able to do that without any data movement. Last distribution type is hash. You can pass in one column or multiple columns now. So this deterministically distributes data into 60 distributions based off of the values or value of the columns in the hash distributions. So on the right-hand side, we have our entire table. This gets passed into a hashing function, and each instance of the same value will always land on the same exact distribution. And that's across any table where it is the same exact value, same column, generic column data type. So for example, like varchar 10, varchar 20, as long as it is a varchar and the same value, it'll be on the same distribution. However, that does not apply for varchar and nvarchar. So it is important to be clean and crisp about defining your data types, because if you kind of have a mix just because of maybe some lazy table creation, even if you have those hashed in the same column, they won't be able to be joined without a shuffle taking place. This is great for maximizing performance, minimizing or eliminating data movement, fast upserts into staging tables, but bad for tables with low cardinality columns. So as an example, imagine you have a 100 million row table and you decide to hash on a column that has 50% null values. That null value is going to get passed into the hash function. And what will happen is that you'll have one single distribution out of the 60 that will contain 50% of your data. And so that's really bad because essentially that's creating data skew in your environment. And each of those 60 possible parallel threads don't have an even workload. And even if you had, let's say, 10% null values, that's still going to mean at least 10% of your data is on one out of the 60 distributions. So you really want to consider high cardinality for key columns, but also evaluating the potential percentage of null values. All right, so same example, but in this case, we have hashed product ID in the order lines table, and we've also hashed product ID in the product table. So now if we look at product ID 2 on the left, we see that it gets hashed into distribution 2. Product ID 2 in this table also gets hashed into distribution 2. So we have the same query. Similar to replicate, the query plan will show that there is no data movement to produce results. Now this query will run faster because the join doesn't need to take place at the compute node level. It can take place on each of the individual 60 distributions. So this will be faster than replicate. Now in terms of general table distribution strategies, when looking at fact tables, really I would always look for a hash distribution candidate. It's going to perform index and particularly improve the performance of building that table. And then if you were to be joining against other dimension tables, typically the dimension is going to be shuffled or broadcast. Dimensions are going to be smaller, so it will have less of an impact. And particularly operations that benefit, like count, distinct, or by partition. Join is really going to have the largest impact from a performance perspective, and also group by. So facts always look for a good hash distribution candidate, and also try to align that with the most expensive data movement of your source tables. So try to align largest source table hash distributions and the target fact table you're landing data into. Dimensions, use replicate for smaller tables too large to store in each compute node. Use hash distribution, and replicate will essentially allow that, when you're ad hoc joining facts and dimensions, it doesn't need to move dimensions around just to perform those joins. With staging tables, I'm going to recommend using hash distribution, particularly for incrementally updated tables. And again, that will greatly improve the performance of doing a incremental upsert operation. Otherwise, replicate if it's infrequently updated, otherwise round robin. And I asked ChatGPT if it could create a decision matrix on picking the right distribution. Its response was essentially there's too many factors to consider and it's impossible. I decided to take a stab at it anyways. So what distribution? Look at first, is the table small? If it is small, is the table updated frequently? If it's not, round robin or replicate is typically going to be a great candidate. But if it is updated frequently, or it's large, you want to evaluate what columns are commonly used in join operations or natural keys with high cardinality. And if there is one, use hash, otherwise use round robin. All right, so next, now one piece that can kind of help with this is Microsoft released a distribution tuning advisor. It's out on their Azure Synapse toolbox. So this is a stored procedure where you can pass in your select statement or run it based off of recently run queries, and it'll produce recommendations for how maybe you should change the distribution of tables. It works pretty well for simple queries, however, not for complex queries. For this demo I'm going to do later, I couldn't even get it to produce any results based off of that query, and always sanity check the recommendation. Right, now let's talk table indexing strategies. So the primary index you're going to want to know in Synapse is the clustered column store index, essentially hybrid table storage format. And I say hybrid because the majority of your data, if it's large enough, is going to be compressed into Parquet-like format, where it's a column store. Whereas the remainder of that data, or as you perform updates or inserts, it's not big enough to compress, will be stored in the Delta store, which is just regular heap storage. Updates or inserts of 100,000 rows per distribution need to take place, and that's 6 million rows for an evenly distributed table, in order for that data to get compressed. So if you're performing what they call trickle inserts, like slowly inserting small amounts of data, it's really not going to be a good candidate for clustered column store, because it's not going to automatically compress that data. Just as an example, let's say we have this table structure on the right, and imagine that's 100 million rows. We define that as clustered column store. Under the hood, it's storing it in this columnar format, where it's storing the distinct values per column. Then let's say we perform a small insert into that table, maybe 100,000 rows. That data will actually get stored in the Delta row store. And that's because it wasn't large enough to meet that threshold to build another row group in the column store. And so it stores it in heap format. And so when you query that table, it's going to add the column store compressed results plus the Delta store compressed results. But this is important to know because depending on your loading pattern or your proc pattern to build a fact, you could effectively not be leveraging the clustered column store index very well. And you may need to build in a process to either rebuild that index periodically, or think about how you can rebuild that table in more of a bulk operation to ensure it gets compressed. So next, clustered index. This is seen as the default index in regular SQL Server. Rows are clustered in the order specified by the index. You have the B-tree index structure. Fantastic, and you do want to be using these in Synapse. I recommend it for most staging tables, particularly anything that is incrementally updated, and that's because it avoids unallocated table space. This can be a performance killer. I've seen environments where staging tables were staged as heaps actually, and tables were incrementally updated. Not a large number of records was changing on a daily basis, but what happened is over a period of months, the underlying footprint of your data grew to a point where it then took facts and dims about 3 times as longer to load. But once we switched those to clustered indexes, so it took care of that unallocated table space, it immediately cut that performance down to the expected levels. And there's just a visual of how the clustered index stores data. Essentially, you have different nodes which have pointers to data pages, which contain the full record, which is ordered by the column or columns you specify for your index. Now, general table indexing strategies. For facts, really always use clustered column store indexes. But with one caveat, avoid updates and deletes. So if you do have facts that are adding in just yesterday's data, performing mass updates, one, I would propose thinking about your process to build that fact in a different and more bulk way. And if you can't, I would not store it as a clustered column store index, because with that, when updates and deletes take place, it doesn't actually remove the updated rows, the old version updated row or the deleted row, it just invalidates it. And then for updates, insert a new row. So if you were to have a 10 million row table and you were to perform an update on every row, your data footprint is now 20 million, even though when you query the data, it will only produce 10 million rows of results. Dimensions, clustered indexes, particularly if you're using a typical type 1 or type 2 dimension pattern that's incrementally built. Leverage incrementally, cluster on the incrementally increasing numeric key like your surrogate key. For staging tables, clustered indexes for incrementally loaded tables. For fully loaded tables, it really could be any of the indexes depending on different query patterns. Okay, essential database settings. So read committed snapshot. So this is, I'm just always amazed when I don't see this enabled on a database, because the alternative I think is just shocking. So just imagine if you have a data engineer and he's running an update statement against a table, that locks the table. Now all read operations against that table, let's say you have business user reporting taking place and it's trying to run a select statement, that select statement would be blocked until that update statement is completed. And that's applicable for any data modification or data definition change operation. So read committed snapshot prevents the reads from being blocked by write operations, reading from a committed snapshot of the data. So always have that enabled. Auto create statistics. So the way that the Synapse, SQL Server, pretty much every other platform, they all create have statistics about the data to better inform generating query plans, such as the number of rows in a table, the cardinality of different columns to estimate when you join them together what might be the resulting rows that are generated. Auto create stats will automatically create those as columns are used in query predicates, and that greatly improves cardinality estimates. And this is enabled in default. They added this sometime after 2020 though. So if your Synapse environment was not created in the last year, I would definitely check this setting because it used to not be on by default. Result set caching. So this will essentially automatically cache the results of any deterministic query in a cache that is managed by Synapse. And by deterministic, I mean, if you run the same select statement, it'll return the same results every single time. Subsequent executions of the select statement, no matter who the user is, will return the results from the query cache. No recomputation is needed, and it doesn't count towards your total concurrency that's possible in the environment. So fantastic feature, essentially just giving you additional possible concurrency and possible better performance. Statistics. So we talked about updating statistics. Key thing I want to highlight here is have a process to update your statistics. If you're only creating them but not updating them, in theory, you would never want to have data updated in your environment, because if data gets updated, the information that the query optimizer has about your data is now out of date, and it could generate a completely horrible query plan. As an example, imagine you have a table, you insert one row into it, auto create stats is on. It'll maintain a statistic that says to the query optimizer, there's one row in this table. Then let's say you insert 1 billion rows into that table, run your, look at your query plan again, it will still think that there's only one row in that table. And because of that, it might decide that it wants to broadcast that data to every single compute node, which would be a massively expensive operation. So have some sort of process. Auto update stats is not supported in Synapse Dedicated Pools. Best practice is really have a stored procedure, and I recommend to run this at the end of updating your staging tables. That will update only outdated statistics after the tables have been loaded. And I say outdated because that'll just make the process more efficient. Because if there's only like a 1% change in the number of rows, you really don't need to update statistics. But it becomes more important as the size of the table grows and the percent of data that's changed. All right, materialized views. So materialized view is going to pre-compute, store, and maintain that data just like it's any other table. On the right-hand side, you can see that syntax. The view automatically gets updated as the underlying data gets updated. So now, for these, there's a couple of scenarios where you would not want to use them. Like if you're using, I would say, stream analytics and you're streaming data into Synapse or another CDC platform where your source tables are churning and updating all the time, I wouldn't use materialized views, because that view is constantly going to be updated, and that's going to be using excessive compute in your platform. Also, just be careful of if you are updating the table definition of a source table used in the materialized view or dropping it and recreating it, you'll actually get blocked because the view will lock changes to the underlying table, or at least the data definition. So you need to disable the view to perform that operation and then rebuild it. Now, the fantastic thing about materialized views in Synapse is that the definition gets indexed. So when query plans are evaluated, it cross-checks your SQL against the indexed view to evaluate whether or not the materialized view could produce the same results as portions of your select statement. So the left-hand side, we have this query that has a pretty complicated CTE. On the right hand, we have this query plan that's generated. You can see that there's a lot of shuffles taking place. It takes about 100 seconds. Now with the same query that's on the left, imagine if we created a materialized view with that CTE definition and hashing on the customer ID, and then run this same query on the left again, you would see that all of those shuffles have now gone away because it has automatically identified that your materialized view definition is the same as your CTE definition, and it automatically replaces that upon execution with the query plan. And so with this query, with the materialized view getting swapped in, that runs in 6 seconds. So materialized views are great for improving performance for, I would say, expensive blocks of code in your SQL. I would not take the approach of defining your dim or your facts as a materialized view, but expensive portions or building blocks of your code, I would evaluate that. Now let's talk about data loading patterns. So patterns to avoid. Let's talk about what is the best way to update, insert, or delete records into an incrementally loaded staging table. CTAS, or create table as select, for an upsert into a table is going to be extremely slow, and here's why. The CTAS is resulting in the entire table being recreated. So if you have a massive table, let's say 1% of the rows are being updated or potentially deleted, you are not moving just 1% of the table or updating just 1% of the table, you are moving and recreating 100% of the table. So instead, I would highly recommend delete and insert with a clustered index on the target table. This will be extremely fast. I recommend wrapping this in a transaction, so begin transaction and commit transaction, and that just ensures that the delete will not be committed unless the insert also succeeds. So it effectively gets processed in one operation. So that we delete from the target where the records meet the join condition, and then we insert everything into the target from our new data that's coming in. And in this scenario, 100 million row table, 1% of data is changing. You would actually only have 1% of data that is physically being moved. So much faster. Just a couple notes on some patterns of writing SQL to avoid in Synapse. Cursors and loops, avoid at all costs. Focus on using set-based bulk operations. And that's really for everything in Synapse. Think bulk. It is a distributed platform. It is not oriented towards transactional processing. It is for analytics, so think bulk, think big data. Scalar valued functions, I'll show an example in a bit of why this is extremely bad. Use table valued functions, multi-step ETL, instead write SQL oriented towards your desired end state. Avoid highly nested CTEs and nested subqueries. CTEs and subqueries by themselves are fine, but avoid lots of nesting. It tends to confuse the optimizer and kind of pigeonhole it into producing unideal query plans. All right, so now we're going to do a optimization demo. And just quick note on how I generated these data sets. So these are TPC DS data sets. So that's the industry standard for performance testing different platforms. The great folks at Databricks, they put together a Python package and notebook to generate these data sets. I essentially just did some refactoring to get it to work in Synapse Spark. So this is out on my GitHub in case you want to go grab that and use it to do some performance testing. All right, so what we have here is 3 tables from the TPCDS data sets: 100,000, 133 million, 28 million rows, so relatively large scale. Let me just make sure this table is dropped. All right, and here's a simple CTAS statement where we are defining based off of a couple joins against these tables with a group by performing some aggregations. So let's look at this query plan. So you'll see here that we have a few different shuffles taking place. This 64% shuffle is moving the 133 million rows, shuffling that around, shuffling the 28 million rows. And if we were to run this, which I'm not, because we don't have 3 hours, it would take 3 hours to produce these results. It will ultimately generate 1 million rows being inserted into this table. So now, something that I noticed in this query plan is that the group by is taking place after all of the data has been shuffled and joined. And if you look at this arrow before the group by, this is estimating that, and I have to draw some columns just to be able to read this number. So 37 billion rows are going to be generated from joining these tables together over 3 terabytes of data. And then that is going to be grouped down into 1 million rows. So I think you can now see why this probably takes 3 hours to run. That is an awful query plan. So essentially what I did on the right-hand side here is I tried to force the optimizer to perform the group by before joining the result sets together. So I rewrote it to have subqueries that are performing the group by on the individual table. So inventory, store sales. And now if we look at this query plan, we are still going to see shuffles taking place. However, key thing to note is now the group by is happening before the join takes place. And if we look at the expected rows going into the group by, that's about 100,000 there, 1 million there, and 1 million there. So we are making our bulk operation smaller instead of having to process a 37 billion row operation. Now, if we were to run this, this would take about 2 minutes. It's a massive improvement, but we aren't done. So let's take a look at this query. One thing that jumps out here, and this was a tip that I had called out earlier, is that we're using a scalar valued function. So we are passing in cost and the price that we sold it for to calculate the margin percentage and then averaging that. And so it is having to, because it's scalar, it is doing a row by row operation. So now, before we look at fixing that function scenario, let's look at if we were to change the distribution of the tables that we are joining here, because these are all round robin right now. So if we were to change all of these to be distributed on the item surrogate key, how would that make our query plan look? So now you can see on the right-hand side, our plan is much less complex. We actually don't see any of these shuffle operations. We have just local group bys and joins that are taking place. And so if we were to run this, we'll see how long this takes. While that's running, this is how I changed the distribution of these 3 tables. This is a proc that I have out on my GitHub as well as on my blog. Essentially just greatly simplifies the process of changing the distribution of a table. This does take a few minutes, so I'm not going to run this. But we'll see that this query will, actually probably won't wait for it, but it'll take about a minute to run. So we've gone now from 2 minutes with having everything as round robin to a minute with everything stored as distributed as hash. I'm going to stop that. So now the table valued function, let's just quickly look at this table valued function definition. So it's kind of a silly function, but just trying to prove a point here. We're passing in these 2 costs and revenue. If revenue is 0, we want to return null. Otherwise, we want to perform a margin calculation. So this is scalar valued because it is not producing the results of a table. So now if we were to rewrite this to be much more performant, we could perform the same thing by returning a table and returning that as a select statement. So we're passing in revenue and cost into a select statement expression. And now on this right-hand side, if we are to rewrite this as a table valued function within that subquery. You'll see that we do have the same query plan, so it's not the best. The query plan doesn't really do a good job in identifying the impact of things like scalar versus table valued. But if we were to run this, you would see that this will run in, I think, about 10 seconds. And you'll notice that I also set the target table distribution to be on the inventory item surrogate key as well. And that's to match the distribution of the source tables that we are using in this query. So now we get about 1 million rows, 17 seconds. So we went from 3 hours down to 2 minutes, down to 1 minute, down to 17 seconds, all via simply thinking about how Synapse works in terms of looking at its distributed nature, leveraging hash distributions, as well as looking at things like how scalar valued functions operate and how we can improve that via writing as table valued. Or, I mean, with this simple of a expression, I would actually just not have that as a function. But all right, so that is our demo. And now we will open it up to questions and answers.